This is the second module in cryptography for the SADIT project. In this module, we will learn a little bit more about cryptography. In the previous module, we looked at the history of cryptography over several hundreds of years and the current state of the standards in cryptography at a very high level. And today we will continue in this lecture on other elements related to cryptography. To start with, here is a brief classification of the different elements, if you want to call it, of the broad subject of cryptology. Cryptology includes both cryptography, which is the art or the science of making encryption algorithms, and cryptanalysis, which is the art or the science of breaking encryption algorithms. And cryptography itself is broken up into secret key algorithms that you see here and public key algorithms that you see here. Now, in secret key algorithms, two communicating parties, if we call them Alice and Bob, they share the same secret key. Whereas in public key algorithms, it's typically an individual who has a public and a private key, and the public key is made public so that anybody can take a look at it. In between, we see this block called hash functions, and hash functions are often used to provide integrity and authentication using cryptographic techniques. Under secret key algorithms, we see two different categories: the block ciphers, which encrypt one block of information at a time, and this block can be a block of letters of the English alphabet, or more typically in today's world, it is a block of bits, zeros and ones. The block sizes are typically 128 bits long. Then you also have a stream cipher, which encrypts information which is arriving in a stream, and these are also typically encrypted in the form of bits. So bits are coming in a stream, and the stream cipher encrypts them into another stream of bits that go up. Under public key algorithm, there are two common categories of algorithms. The first one uses what is known as integer factorization, where you're trying to factorize or find the prime factors of a large composite number. The second category of public key algorithms, they make use of an idea called discrete logarithms, which is, suppose you raise a number to the power of another number, you know what the result is going to be, but finding out what that power is or the exponent is not easy under certain circumstances, and this property is used in some public key algorithms. This is the conventional encryption model, which deals with the confidentiality of information or data. So we have two communicating parties. We will call them Alice and Bob, and they are communicating over a channel that is not very secure. And what Alice does is she has a piece of data, or data which is broken up into pieces, blocks, if you want to call them, and each block is represented by this variable x, which is called the plain text. She takes a block x and she encrypts it with a key k that you see here. The encrypted data block is called y, and this is called the ciphertext. Y is sent over the channel that is not secure. When Bob gets y, Bob is able to decrypt the information or the data which is contained in the ciphertext y using the same key k. You can see that the two keys here, k, that are used by Alice and Bob, they are the same, namely k. And when Bob decrypts y, the ciphertext, he gets back the plain text x here. What we will not explore in this module is how this key k is generated. So there's a key source and there's a secure channel. You see that there's a channel here called the secure channel. So this could be Alice and Bob meeting in a coffee shop, for example, for the time being, where they exchange or set up this key k. We will come back to this perhaps later to see how such key establishment can be done. So with regards to confidentiality, the problem here is that they are trying to protect the contents of X. And the model that we are looking at here assumes that there's a bad guy, typically called Oscar. Looks like a kid here, but today we know that there are all these criminal organizations as well trying to find information, like credit card information, whatnot. And this Oscar is able to look at the ciphertext only for the time being. And when Oscar looks at the ciphertext, the purpose of encryption is to ensure that the information X is not leaked to Oscar. So this is what confidentiality implies in this particular case. So just to recap everything that I said, in conventional encryption, you have an algorithm E, which uses a key K. And what this algorithm does is it takes as input a plain text X, and its output is Y, which is the ciphertext. Similarly, there's an opposite algorithm, an inverse of this algorithm E, which is called D. And what the algorithm D does is it takes as input the ciphertext Y, uses the key K, and it produces the plain text X. K is the encryption and decryption key. Gen, which you saw in the previous slide, is the key generation algorithm. And the functions E and D are inverses of one another. So for example, if you encrypt dk of Y, ek and dk get cancelled and you get Y. Similarly, if you decrypt ek of X, they get cancelled and you get X. And the last one is tricky. You are encrypting the decryption of X, but theoretically speaking, it is the same process here, which means that this E and the D, they get cancelled and you end up with X here. So practical crypto systems, for example, the algorithm E, they must be efficient to implement. It should not be that somebody needs a Cray computer in order to encrypt a block of data, or a Cray computer to decrypt a block of data. These things should be easy enough to do. If Oscar sees the ciphertext Y, theoretically speaking, there should be no information that Oscar gets. He should not be able to find the plain text X. He should not be able to find the key K. And this is where cryptanalysis comes into the picture, which is the art of breaking these encryption schemes. So cryptanalysis involves attacks against an encryption algorithm. So what do we really mean by breaking an encryption scheme? Without getting into the formal mechanisms and methods that people have described in the literature, at a high level, what we assume here is that the bad guy Oscar, when he breaks the encryption scheme, is able to recover the plain text from the ciphertext. And if that's all he does for a particular instance, this might be okay. But oftentimes, breaking the encryption scheme implies that Oscar has recovered a key. And if the key has been recovered, Oscar can use that key to break many ciphertexts. Oftentimes, you don't need an encryption scheme to be broken. When we are using protocols, there may be vulnerabilities in the protocol that bypass the encryption scheme. So many of the attacks that we see or we have heard of in recent times, they do not actually break the encryption scheme. If you take the target attack, DDoS is not broken. But there are software problems or other vulnerabilities in the protocol that make networks and systems not very secure. But here is one formal principle that people use in order to test encryption schemes. So given an encryption algorithm ek of X, which is equal to Y, Kirchhoff's principle, which is very commonly applied in cryptography, assumes that the bad guy Oscar knows the algorithm. And the only thing that the bad guy does not know is the key K. There are some implications of this, and the first implication of this is that you should not hide the encryption algorithm, because if you think that you're going to be secure because your encryption algorithm is hidden, this is unlikely to be the case. Oftentimes the algorithms get leaked, and if there are some weaknesses in these algorithms, then the bad guys can quickly exploit them. But what it also says here is that since Oscar does not know the key, he can make some intelligent guesses. He can try to exploit any known weaknesses of the algorithm. But most importantly, if there are only a small set of keys, so Oscar knows that there are like this 10 odd keys that anybody can use, then he can try each one of them. And this is called a brute force attack, where you try every possible key. And the number of keys and the set of all possible keys is called the key space. The number of keys is how many keys are there in this set. And So one of the techniques that people use today is to make the key space very large, which means that you have so many possible keys that it is fairly difficult for Oscar to do a brute force search of all the keys. A shortcut also in this algorithm can allow Oscar to recover the key. So you need to make sure that there are no trapdoors or shortcuts in these algorithms that people have implemented. There are many different types of attacks that people talk about, and the attack that we have looked at or we have talked about in the previous diagrams is the so-called ciphertext only attack, in which case Oscar is observing the channel that is not secure and he has a set of ciphertexts, and we can call these ciphertexts as y1, y2, y3 all the way till yn. So he has a certain number of ciphertexts and his objective is to find the key or break the encryption scheme so that he is able to recover some of the plain text. A more common attack is called the known plain text attack. Here, Oscar not only knows the ciphertext, but he also knows the plain text xi for a certain number of plain text ciphertext pairs. And this is possible because Oscar can make intelligent guesses, and certain plain texts are kind of obvious. For example, if you have an IP protocol or IP packet, the header in the packet can be guessed because there are some fields there like source IP address, destination IP address, version numbers, and so on that can be guessed. So the known plain text attack is commonly used to test whether an encryption scheme is good enough. In the same way, you can imagine a chosen plain text attack. Here, Oscar can choose the plain texts that are going to be encrypted. Imagine that there's a black box and Oscar inputs these plain texts and he obtains the ciphertext, and his goal is to find the key, which he's unable to do right now. And because some plain texts provide more information about the key than others, the chosen plain text attack is a little bit stronger than the known plain text attack. There's an adaptive chosen plain text attack where Oscar can adaptively change his plain text. So he tries a particular plain text, gets the corresponding ciphertext, and he decides, okay, now maybe if I try this plain text, this is going to give me some extra information because I know something about the algorithm. Remember that he knows the algorithm because of Kirchhoff's principle. The chosen ciphertext attack is the opposite of the chosen plain text attack. Here he has a black box that does decryption, and so he can enter different ciphertexts and get the corresponding plain text, but he still doesn't know the key. And his objective is, in this case, of course, to find the key. The chosen text attack is a combination of both the chosen plain text and the chosen ciphertext attacks. Most commonly, people talk about the chosen plain text attack or the known plain text attack. Of course, there are a bunch of other security attacks that you can imagine which are not so technical. For example, there's a well-known replay attack where you don't break the encryption scheme, you don't decrypt anything, but you repeat the encrypted message, and this causes either confusion or it helps you deduce certain information if you are the attacker. And this is called the replay attack. A very common attack that people might have seen in the mass media is the so-called man-in-the-middle attack. So the idea here is that you really don't break the encryption scheme, but you sit in the middle of a key establishment protocol between Alice and Bob. And then you intercept the messages that they're exchanging to establish the keys, and you create a set of compromised keys. So Alice and Bob don't know that the key has been compromised to Oscar, and they continue to use the protocol assuming that everything is fine, but Oscar has the key, so he doesn't really have to break the encryption scheme because he has found the key by bypassing the encryption scheme. And finally, of course, you have the traditional attacks like blackmail, bribery, torture, and so on, which you can use to find keys if you are a bad guy, perhaps. And so with this, we conclude the second module, which gives you some idea of the terminology that people use when they talk about encryption.